Welcome to G Fun Facts Online. Today, we are stepping into the microscopic cathedral of the universe to witness a moment that physics has been chasing for over 100 years. For over a century, the atom has been the ghost in the machine of our reality. It is fundamental and omnipresent, yet it has remained perpetually elusive. We have inferred the existence of atoms through mathematical elegance. We have smashed them apart in cyclopean colliders to study their debris. We have trapped them in electromagnetic cages to glimpse their shadows. We have even arranged individual atoms into corporate logos, using scanning, tunneling microscopes, moving them around like children playing with blocks. But until very recently, we had never seen them as they truly are in nature. We had never seen them wild, untethered, and dancing to the chaotic tune of quantum mechanics. That changed in May 2025. In a laboratory at the Massachusetts Institute of Technology, a team of physicists led by Professor Martin Svierlein achieved what was long considered impossible. They captured the first ever images of individual atoms moving freely in space. They didn't just see a single isolated atom held static in a trap. They photographed a chaotic, swirling cloud of them, interacting, bumping, and pairing off in real time, effectively freezing the quantum dance mid-step. This breakthrough is not merely a triumph of imaging technology, it is a philosophical watershed. For the first time, the weird, probabilistic nature of quantum mechanics, the spooky action that Einstein debated and Schrödinger immortalized with his cat, has transitioned from abstract equations on a chalkboard to visible, tangible reality. We are no longer just calculating the quantum world, we are watching it. To understand the magnitude of seeing an atom in the wild, we must first appreciate the Herculean struggle to see anything at that scale at all. The concept of the atom began not as science, but as philosophy. The Greek thinker Democritus, in the 4th century BCE, proposed a thought experiment. If you cut a piece of cheese in half, and then in half again, eventually you would reach a piece so small it could not be cut. He called this the atomos, or the uncuttable. For 2 millennia, this remained a mere idea. Matter looked continuous to the human eye. Water poured, wind blew, and stones stood solid. There was no visual evidence of a pixelated universe. By the 19th century, chemistry demanded atoms. John Dalton's ratios and Dmitri Mendeleev's periodic table made no sense without discrete units of matter. In 1827, botanist Robert Brown noticed pollen grains jittering in water. This Brownian motion was later proved by Einstein to be the result of invisible water molecules battering the pollen like an unseen crowd pushing a beach ball. We knew they were there, but they remained invisible. The problem was light itself. To see an object, you must bounce a wave off it. If the object is smaller than the wavelength of the wave simply washes over it like a tsunami over a pebble. Visible light, with wavelengths between 400 and 700 nanometers, is thousands of times clumsier than a single atom, which is roughly 0.1 to 0.5 nanometers wide. Trying to see an atom with a standard microscope is like trying to feel the braille on a page while wearing boxing gloves. The 20th century brought solutions like electron microscopes and scanning tunneling microscopes. These machines famously produce the image of 35 xenon atoms, spelling IBM. But there was a catch. These methods required the atoms to be held essentially motionless, often locked in a crystal lattice or pinned to a surface, chilled to near absolute zero, and scrutinized over time to build up an image. We were taking long exposure portraits of statues, not snapshots of runners. We saw the structure of matter, but not its behavior. The wild atom, the particles zooming through space, colliding and interacting, remained a blur. Why is a moving atom so hard to photograph? The answer lies in the heart of quantum mechanics, specifically the Heisenberg uncertainty principle. Formulated by Werner Heisenberg in 1927, this principle states that you cannot simultaneously know the precise position and the precise momentum of a particle. The more accurately you know where it is, the less you know about where it is going. When atoms are in the wild, moving freely in a gas, they are governed by this principle. They act less like billiard balls and more like fuzzy clouds of probability. If you try to shine a light on them to see them, the photons carry enough energy to knock the tiny atoms off course, changing the very behavior you are trying to observe. As Professor Svierlein noted, if you took a flamethrower to these atoms, they would not like that. Standard imaging of atomic clouds before 2025 involved absorption imaging. Scientists would shine a laser through a cloud of atoms and look at the shadow cast on the other side. This gave the overall shape of the cloud, like seeing a flock of birds from a distance, but the individual birds were lost in the fog. To see the individuals without destroying the flock required a completely new paradigm. The breakthrough at MIT utilized a technique dubbed atom-resolved microscopy. It is a sophisticated trap-and-release mechanism that functions like a high-speed strobe light for the quantum world. The experiment began with a vacuum chamber, emptied of almost all matter to prevent interference. Inside, the team used magnetic fields and lasers to cool a gas of atoms, specifically sodium and lithium, to ultra-cold temperatures, mere billionths of a degree above absolute zero. At these temperatures, the thermal jitter of atoms slows down enough for quantum effects to dominate. This cooling process is incredibly complex, utilizing a method called Raman sideband cooling, which uses lasers to kick the atoms into a lower vibrational state, removing almost all their kinetic energy. Unlike previous experiments where atoms were locked in a grid of light called an optical lattice from the start, the MIT team started with a loose trap. Imagine a shallow bowl where marbles can roll around. The atoms were confined to a general area but were free to move, collide, and interact within that space. This was the wild phase. They were free-range atoms, living out their quantum lives. To take the picture, the researchers couldn't just snap a shutter because the atoms moved too fast relative to their size. Instead, they employed a two-step freeze technique. First, the lattice clamp. Suddenly they activated a high-power optical lattice. This is a grid of laser beams that creates a series of wells or egg cartons of energy. This lattice was turned on so abruptly that it trapped the atoms exactly where they were in that split second. The wild motion was instantly arrested. The atoms were pinned to the nearest grid point of the laser light. Second, the flash. Once the atoms were pinned, and thus could no longer blur the image by moving, the team blasted them with a specific resonance of laser light. The atoms absorbed this energy and re-emitted it as fluorescence. They glowed. Finally, a highly sensitive microscope objective lens gathered this faint glow, recording the position of every single atom on a digital sensor. The result was a map of exactly where every atom was the moment the music stopped. It was a snapshot of a dynamic system, revealing the hidden structure of chaos. The team didn't just photograph any random atoms. They chose their subjects carefully to test the fundamental laws of the universe. They imaged two distinct types of particles, bosons and fermions. In the standard model of physics, all particles fall into one of these two camps, and they have radically different personalities. Bosons are the party animals of the particle world. Named after physicist Sachendra Nath Bose, they have an integer spin. Their defining characteristic is that they love to be in the same state at the same time. If you cool a group of bosons down, they will all try to pile into the exact same low-energy state, effectively merging into a single superatom. This is the famous Bose-Einstein condensate. In the MIT photos, the researchers used sodium-23 atoms, which are bosons. When they looked at the images of the free-range sodium, they saw bunching. The atoms weren't distributed randomly. They were clumping together more than simple chance would predict. They were showing a preference for proximity. On the other hand, we have the antisocial fermions. Named after Enrico Fermi, they have half-integer spins. They obey the Pauli Exclusion Principle, which states that no two fermions can occupy the same quantum state simultaneously. This is the rule that keeps matter solid. It prevents the electrons in your hand from collapsing into the electrons of the cup you are holding. For this test, the team used lithium-6 atoms. The images revealed the opposite of bunching. The lithium atoms maintained a respectful distance from one another, creating a hole around each atom where no other identical atom could be found. It was a visual confirmation of the force that keeps the universe from collapsing on itself. Perhaps the most visually stunning result of the MIT experiment was the direct observation of the de Broglie wave. In 1924, Louis de Broglie proposed that matter, like light, acts as a wave. He suggested that every moving particle has a wavelength associated with its momentum. For a baseball, this wavelength is infinitesimally small and irrelevant. But for a cold, slow-moving atom, the wavelength can be larger than the atom itself. When the MIT team imaged the bosons, they analyzed the distance between the particles. They found that the clumping happened in a wave-like pattern. The probability of finding a second boson near a first one rippled outward. By analyzing the positions, they could literally trace the shape of the matter wave. They saw the physical manifestation of the equation that won de Broglie the Nobel Prize. They were not looking at balls of matter. They were looking at ripples in the quantum field, frozen in time. The study went deeper than just confirming old theories. It shed light on one of the most mysterious processes in physics, Cooper pairing. Superconductivity, the ability of electricity to flow with zero resistance, relies on electrons, which are fermions, pairing up. Since fermions normally repel each other, they need a mechanism to overcome this dislike and bond. In conventional superconductors, they use vibrations in the crystal lattice to glue themselves together. But what happens when there is no lattice? Can fermions pair up in empty space? The MIT team created a gas of lithium fermions with two different spin states. While identical fermions repel each other, opposite fermions can attract. By tuning the magnetic fields, the researchers increased the interaction strength between these two groups. The images showed something remarkable. The fermions began to form tight pairs in the void. They weren't bound into molecules in the chemical sense. They were bound by quantum correlations. The images showed these pairs swirling around each other, a precursor to the superfluid state, where flow becomes frictionless. This is the first time scientists have been able to see these pairs forming in real space. It is a reminder that physics is about physical things. Why should the average person care about photos of lithium and sodium atoms? The implications ripple outward from the lab into the future of technology and our understanding of the cosmos. First, let's talk about high-temperature superconductors. The holy grail of material science is a room-temperature superconductor. Currently, superconductors only work at extreme cold or extreme pressure. If we could create wires that carry electricity with zero loss at room temperature, it would revolutionize energy grids, transport, and computing. The pairing observed in the MIT experiment mimics the mechanism believed to happen in high-temperature superconductors. By visualizing how these pairs form and move in a simplified, controllable gas, scientists can simulate and test theories that are impossible to verify in complex solid crystals. The wild atoms act as a quantum simulator, a wind tunnel for electrons. Then, there are neutron stars on a chip. Neutron stars are the densest objects in the universe besides black holes. They are essentially city-sized balls of neutrons, which are fermions. The physics governing a neutron star is remarkably similar to the physics governing the ultra-cold lithium gas in the MIT experiment. Both are systems of strongly interacting fermions. Obviously, we cannot fly to a neutron star to see what is happening inside. But by studying the wild lithium atoms, we are effectively modeling a neutron star on a microchip. The images help us understand the equation of state of nuclear matter, showing how matter behaves under densities, where the usual rules of chemistry break down. This also impacts quantum computing. Quantum computers rely on entanglement, the spooky connection between particles. The biggest challenge in building them is decoherence, where the environment disturbs the delicate quantum state. The MIT technique allows for precise monitoring of how atoms interact with their neighbors. This could lead to better error correction codes and new ways to arrange quantum bits that are more robust against noise. Finally, this opens the door to new states of matter. When you allow atoms to move freely and interact strongly, they can form phases of matter that don't exist in standard solids, liquids, or gases. We might discover supersolids, which are rigid but flow like liquids, or exotic magnetic states. Having a camera that can snap a picture of these states is the first step to understanding and, eventually, engineering them. The first photos are just the opening shot. Now that the technique has been proven, the floodgates are open. Currently, the process is destructive. The imaging technique heats the atoms and scatters them, so you only get one snapshot of one specific cloud. The next frontier is non-destructive imaging, or at least rapid-fire sequencing, where scientists could stitch together a movie of quantum dynamics. Imagine watching a Bose-Einstein condensate form in real time, seeing the chaotic gas suddenly snap into a unified wave. There is a profound beauty in the images released by the MIT team. They look like pointillist paintings, scattered dots of white against a black background. To the uninitiated, they might look like static on a TV screen. But to a physicist, they are the face of the Hamiltonian. For decades, quantum mechanics has been taught as a theory of limitations. We are taught what we cannot know. We are taught that particles are abstract wave functions until measured. This creates a mental distance. We treat the quantum world as a mathematical fiction that only coincidentally overlaps with our reality. These photos bridge that gap. They show that the wave function is not just a bookkeeping tool. It is a physical shape that matter takes. They show that the exclusion principle is not just a rule, it is a visible force field around a particle. When we look at the bunching of the bosons, we are seeing the gregarious nature of the universe. When we look at the spacing of the fermions, we are seeing the individualism that allows structure to exist. We are seeing the raw code of reality rendering on the screen. The phrase atoms in the wild is apartment. For most of scientific history, we have studied atoms in captivity, domesticated, frozen, isolated, and forced into artificial lattices. We learned a lot from these zoo animals. But we always knew that out in the open, in the chaotic freedom of a gas or a fluid, they were doing something different. The images captured in 2025 are our first safari into the quantum wilderness. We have proven that we can track the beasts without killing them until the very last moment. We have confirmed that the map drawn by Schrödinger, Heisenberg, and Fermi matches the territory. As we stare at these speckled photographs, we are reminded of the famous pale blue dot image of Earth. Just as that photo recontextualized our place in the cosmos, these photos recontextualize our understanding of matter. We are not solid. We are not continuous. We are vast collections of tiny, vibrating, interacting probabilities, dancing a complex waltz in the dark. And finally, someone has turned on the lights. Thanks for listening to G Fun Facts Online.